Let's talk about how we solve equations involving radicals such as square roots and cube roots and so forth. To do this, we're going to use the following fact, the following theorem, and it's in the same sort of style as the theorem that told us about when we can add and subtract the same thing to both sides of an equation without changing its solution set. Now, unfortunately, it's not going to be quite as powerful as those because it's only going to give us sort of one direction of the relationship. We're not going to get exactly equivalent equations, but there will be a strong relationship here. So the theorem says that if the square root of a equals b, where here a and b are expressions, then we can basically square both sides. And we can think about what happens if we take the square of both sides. Now, square and square root cancel each other out, mostly. So if the square root of a equals b, then a equals b squared. So we could think of this as squaring both sides of an equation. However, notice that this only goes in one direction. We only have that if a square root of a equaled b to begin with, then a equals b squared afterwards. Now, what this means for us is the following. To solve an equation involving a radical, you must first isolate the radical on one side of the equation. Step 2, raise both sides to a power to cancel the radical. And then once again, we have an absolutely essential check your answers. Because extraneous solutions, that is solutions that come up as we go through the process, even if we don't make any mistakes, but aren't solutions to the original equation, are possible. So extraneous solutions may arise, even if you haven't done anything wrong. So we have to check our answers every single time we want to solve an equation involving radicals, because it's very common to run into a situation where you get an answer or maybe many answers, and some of them will be correct or maybe none of them will be correct. So you do need to check your answers completely. So let's take an example where we use this technique and where we make sure to check our work afterwards, make sure we didn't get any extraneous solutions. So let's try to solve the equation square root of x plus 6 minus 5 equals 4. So we want to find the values of x that will make this equation true. So remember that step 1, we want to isolate the square root expression. And so in this case, we'll go ahead and do that by adding 5 to both sides. Adding 5 to both sides gets the square root of x plus 6 term on the left by itself. Step 2, we want to raise both sides to powers that cancel the radical. Now, the way that you know which power to use is by looking at the index of the radical. Now, this radical doesn't have an index written, which means it's got an invisible 2 sitting there. We call this a radical with index 2 because we're looking at the square root. On the other hand, if we were looking at a cube root, that would have a written index 3, or we could look at the 4th root, the 5th root, etc. So these are the numbers that we want to look at that will cancel out the radical. So at this point, what we want to do is we want to square both sides of the equation. Now, when we take the square root and then square it, those two functions cancel each other out. And so we're left with x plus 6 on the left, because the squared and the square root annihilated each other. And on the right, we have 9 squared, which is 81. So at this point, we've managed to turn our equation involving a radical into one that's really just linear, and in fact a very simple linear equation as well. We'll just want to subtract 6 from both sides to get x is equal to 75. And we want to claim that that's our solution. But before we can do that, before we can give our answer, we have to go back and check it, because extraneous solutions show up all the time. So step 3 is we check our work. So we'll look at the square root of, and now we'll plug 75 in for x. We'll say, does that left-hand side of the original equation equal the right-hand side of the original equation? And we're just going to simplify the two sides without moving anything around or doing any algebra. So 75 plus 6 is 81. The square root of 81 is 9. And 9 minus 5 does in fact equal 4. So that checks out. So now we can write down that our solution set is the number 75. So now we can say that the 75 we found before is in fact a solution, because it checks out when we move to the step 3, where we check our solutions. All right, so that was the most basic example of solving a radical equation. Let's look at another one. Let's look at the square root of x minus 4 plus x equals 6. Now this one's a little bit different because we've got variables both inside and outside the radical. Getting rid of the radical is the first priority. We can't solve for a variable if it's still inside the radical, just like we can't solve for a variable if it's in the denominator of a fraction. And so our first goal is always to get rid of that radical, even if it makes the rest of the problem more complicated. So the first thing that we're going to do is we're going to isolate the radical by itself on one side of the equation. Then we're going to square both sides of the equation and see what we get. The square root and the squared cancel each other out. And so we're left with x minus 4 on the left. And then on the right, we have 6 minus x squared, which is 6 minus x times 6 minus x. And if we multiply all of that out, we'll get 36 minus 6x is minus 12x plus x squared. So now we can subtract x from both sides and add 4 to both sides to get 0 on one side. And we want to do that because our new equation is a quadratic equation, which means to solve it, we're going to need to use the zero factor theorem or the quadratic equation or something, and in any of those cases, we need 0 on one side. So now we've got this equation. Let's go ahead and rewrite it in standard form, where we write the terms in decreasing degree order. So x squared minus 13x and plus 40. Now, to factor this, we need to find two numbers that added to equal negative 13 multiplied to equal 40. Fortunately for us, such numbers exist. So we get x minus 8 and x minus 5 as the two numbers. Negative 8 plus negative 5 is negative 13. Negative 8 times negative 5 is positive 40. And so we get this equation here. So we get that 0 is equal to x minus 8, or 0 is equal to x minus 5. And if we add 8 to both sides, we get 8 is equal to x, or 5 is equal to x. Now again, we have to plug these into the original equation to see whether or not they work. So let's check. Let's first check x equals 8. If we plug 8 into the equation, then we ask, is 8 the square root of 8 minus 4 plus 8 equal to 6? Well, simplifying this, that will be the square root of 4 plus 8, and we ask, is that equal to 6? Square root of 4 is 2, and so we ask, is 2 plus 8 equal to 6? And it's just not. 2 plus 8 is 10. 10 is not equal to 6. So that doesn't work. So that means that x equals 8 is not a solution. We're going to eliminate that one. Now, we didn't do anything wrong. There was nothing we really could have done throughout this process to have avoided concluding that x equals 8 was a possibility. There are some subtle theoretical reasons, actually, why 8 does have some meaning. It's not totally random, but it's not a solution to the problem. And so there's no way we could have seen that without checking back in the original equation. So we have to make sure that we do that every single time we do a problem like this. So x equals 8 is something that our math suggested might be a solution, but going back to check, it's not. It's sort of an artifact of the technique that we used to come up with our solutions. Now we still need to check x equals 5. We're not guaranteed that every equation has a solution. It could be the case that both of these equations are extraneous, and we're not going to know that until we go back and check. So we're going to need to check x equals 5 in exactly the same way. If we plug 5 in, we get the square root of 5 minus 4 plus 5. We ask, does that equal 6? Well, the square root of 5 minus 4 is the square root of 1 plus 5. And we ask, does that equal 6? Well, yes, this one does, because the square root of 1 is 1, 1 plus 5 is 6, and so that checks out. So that means that x equals 5 does work for us, and so our solution is x equals 5, or the solution set containing just the number 5. So this problem had only one solution to it. It's possible for these equations to have two solutions or to have no solutions. So we should be very careful when working with these. Let's do another example. let's look at 3 minus the square root of x plus 1 equals 5. So once again, we want to isolate the radical. We have to do that first. We get negative square root of x plus 1 equals 2 after subtracting 3 on both sides. We need to get rid of this negative. We can do that by dividing both sides by negative 1. Or we could multiply both sides by negative 1. That would work too. Negative divided by negative is positive, so we get the square root of x plus 1 equals negative 2. So now we're going to square both sides and get x plus 1 equals negative 2 squared is 4. Now we can subtract 1 and get x equals 3 as our potential solution. Of course, we need to check this. So we can check and say 3 minus the square root of 3 plus 1. Does that equal 5? So we get 3 minus the square root of 4. We ask, does that equal 5? And we get, that means 3 minus 2. We ask, does that equal 5? And it doesn't. It simply doesn't. So the only solution we found, the only possible solution, I should say, that we found to this problem was 3. If anything was a solution to this problem, 3 would be. But 3's not. 3 is not a solution, which means that the equation 3 minus the square root of x plus 1 equals 5 has no solutions. And we write that the solution set is the empty set. That is the set containing no elements. There's nothing you could possibly put into this equation that would give you a true statement out of it. Now, this is in fact something that we could have seen at a point earlier in the process. Something that you can watch out for. We didn't have to see it, as you saw. We still got the correct answer. But think back to, at one point we had the following equation. We had the equation square root of x plus 1 equals negative 2. Well, actually, this type of equation we know can never happen. And this can never happen since the square root of something is always, well, if it's a real number, is always greater than or equal to 0. The square root of a real number can never give you a negative number. And so if we ever run into a point in our problem where we need the square root of something to equal a negative number, well, then we know we're done. We know that that's not possible at all, because the square root can never equal a negative number. Now, like I said, that can shorten some of your problems. That can give you an occasional quick road to the answer when the answer is no solutions. But you don't need to have noticed that. If you just follow the process and make sure to check your answers every single time, then you will get to the right answer also. That will also work. All right, the next thing that I want to talk about is what happens when you've got more than one radical in a problem. And this is where it does get a little bit complicated, to be fair. So let's suppose that we have the square root of x plus 1 minus the square root of x minus 1 equals, let's say 4. So here we've got two different radicals, and we can't combine them together or anything like that, at least not in any obvious way. So the thing to do in a situation like this is to isolate one of the radicals. We're going to isolate one of the radicals, then raise both sides to a power, and go from there. So in this problem, I'll go ahead and add the square root of x minus 1 to both sides of this equation in order to isolate the square root of x plus 1. So we'll get the square root of x plus 1 is equal to 4 plus the square root of x minus 1. And this is what we'll raise both sides to the second power on. So on the left, we get something easy. This just gives us x plus 1. On the right, though, we've got some work to do because this is 4 plus the square root of x minus 1 times 4 plus the square root of x minus 1, and we have to distribute all of that out. So 4 times 4 is 16, and then we get 4 times the square root of x minus 1 plus 4 times the square root of x minus 1. I've got a little mistake there. It's x minus 1 in both cases. And then plus, I'll go ahead and write this term over here as the square root of x minus 1 squared, because we've got the same term in the second place for both of those factors that we're multiplying together. So simplifying things down, we get x plus 1 equals 16 plus 8 times the square root of x minus 1, because those two middle terms are like terms. But now we've got the square root of x minus 1 squared. Well, we know what that is. That's what we've been working with. That's the type of expression we've been working with. And the square root of x minus 1 squared is just x minus 1. The square root and the squared cancel each other out when they're written like this. So now we have x plus 1 equals 16 plus 8 times the square root of x minus 1. Sorry, I wanted to simplify this a little bit because we have some like terms. We've got a 16 and a negative 1 gives us a 15 actually, and then plus an x, and then plus an 8 square root x minus 1. Well, now what do we have? We've got an equation which involves a radical. And so we can continue on from here. At this point, we can sort of forget what came before. For the moment, we'll still have to go back and check our work once we get to some solutions. But we can treat this as if it were a brand new problem. And if it were a brand new problem, then what we would want to do is isolate the radical, get the radical by itself. So we'll go ahead and start doing that. We'll subtract x from both sides. We'll subtract 15 from both sides. And so we'll get negative 14 is equal to 8 times the square root of x minus 1. And now here's where we can actually stop. We can use the same trick that we had last time. The square root of x minus 1 is going to be greater than or equal to 0. It's going to be non-negative. 8 is a positive number, which means that 8 times the square root of x minus 1 is going to be a non-negative number. It's going to be greater than or equal to 0. But negative 14 is less than 0. So that tells us that this equation has no solutions. And therefore, the original equation has no solutions. So our answer to the original problem is no solutions. There's no number that you can put into this equation, square root of x plus 1 minus square root of x minus 1 equals 4, that will give you a true statement out of it. Now, if you did continue by the same process that we had before, you would eventually get to some value of x, but when you tried to plug that into the original equation, you would get a false statement out of it. You would get a statement that isn't true, and therefore you would also figure out that there are no solutions. However, this way is a little bit faster. It does shortcut things a little bit. All right, the last topic from this section is what we do when we've got equations that might have some radicals, might have some rational powers of variables. And one of the techniques that we can sometimes use is to do a substitution. So let's consider the following example. Let's look at x to the fourth plus 5x squared plus 4 equals 0. Now this is a degree 4 polynomial. We haven't looked at any degree 4 polynomial equations so far. And we haven't looked at any sort of formulas for it. We haven't even looked at any strategies for dealing with them yet. And we're not going to look at any general strategies for dealing with degree 4 polynomial equations because they tend to be pretty complex. However, if we are on the lookout, we can occasionally spot situations where we can make things easier by use of a clever substitution. Now, a substitution is what happens when you, the person working the problem, introduce a variable to stand for some expression involving the existing variables. Now that's pretty vague, but that's pretty vague because it's a very flexible type of idea. We can introduce new variables actually whenever we want, and we can define them however we want, and sometimes, if we do that cleverly enough, we can solve problems that we couldn't otherwise. So this example right here with x to the fourth plus 5x squared plus 4 equals 0, we haven't seen anything exactly like this with the x to the fourth, but we've seen things that look sort of like this. This looks like our quadratic equations. And in fact, by using a substitution, we'll be able to write it as a quadratic equation. And the key to that is noting the following. We can write x to the fourth as x squared squared. We're just rewriting the existing equation. It's the same equation. I'm just writing x to the fourth as x squared squared. Now the reason why I'm doing this is because now I notice that this x squared here and this x squared here are the same. And in fact, if I were to sort of treat these boxes as if they were filled in and as if they were their own variable, this would look like a quadratic equation in the variable blue square. Now, we're not going to write it down exactly that way. We're going to write it down in a a way that's easier to read, but that's the idea. If we took this x squared and treated it as a single object rather than as the power of something, then we would have that object squared plus 5 times that object plus 4 equals 0. And that behaves like a quadratic equation that we're used to. So what we can do is the following. We can do a substitution. We can let some new symbol, I'll use the symbol z, equal x squared. We can introduce a new symbol and have it be whatever we want. But if we happen to notice that x squared is behaving sort of like its own single variable here, then we can use a new symbol to represent it so that we get the equation z squared plus 5z plus 4 equals 0. So if z is x squared, then the solutions to the original equation are related to the solutions to the equation involving the z's. Now, the equation involving the z's, we know how to solve. This is just a quadratic equation. And in fact, this is one of the nice ones that actually factors. So we can factor this equation as z plus 4 times z plus 1 equals 0. And so we can use the zero factor theorem to say that, therefore, z plus 4 equals 0, or z plus 1 equals 0. But that means that z equals -4, or z equals -1. So this is great. We were able to solve the equation in the z's. We were able to figure out what z has to be equal to in this problem, but that doesn't actually solve the original equation. The original equation was looking for the solutions involving the x's. Well, here is where we go back. So now we go back to the original variable. And it's going to often be useful to treat each one of these z solutions separately. So if z equals -4, what does that mean about the x's? Well, we look back to where z was defined. We let z equal x squared. So if z is equal to -4, that means that x squared is equal to -4, because x squared and z are the same thing. And now we can solve this equation for x. And write this as, well, if x squared equals -4, the square root property says that that means that x is equal to plus or minus the square root of -4, which we can simplify. This is plus or minus the square root of 4i, which we can simplify further to x is equal to plus or minus 2i. So that gives us some solutions for the original variable, x. Let's do the same thing with -1. If z equals -1, then that means that x squared equals -1, which means that, again, x is equal to plus or minus the square root of -1, and the square root of -1 is just I. Now, you always, of course, want to check your work. I'm going to skip that for this problem, but whenever you do a substitution, you do want to definitely check your work every single time. But in this case, it turns out that all of these potential solutions that we have are actually solutions. So our answer, which I'll write up here at the top, we have that x is equal to plus or minus 2i or plus or minus I. The solution set, which you should always write out completely without using plus or minuses, is 2i, negative 2i, I, and negative I. So that's a way that we can use substitution to solve a problem. We'll do a couple more, or one more example. I just want to point out one more pattern that we notice here. In this case, we started with a degree 4 polynomial. And how many solutions did we get? Well, we got 4 of them. The pattern continues, and for any degree n polynomial equation, you get at most n solutions, and in fact, in some sense, you usually get the full set of n solutions. So if you were to take a random degree 4 polynomial equation, more than likely you would have 4 solutions. Actually finding those is a challenge, but that is what you expect. All right, let's do one more example, slightly different, but with the same idea. Let's look at the equation x minus 6x to the 1/2 minus 18 equals 0. Now here we can try doing the same thing, only instead of writing x squared as a new variable, in this case it's going to work out for us to use x to the 1/2 as the new variable. Now I can't tell you a strategy that will always let you know exactly what substitution to use. This is something that takes a lot of practice and some experience to do efficiently. But in this case, a substitution like the following will help a lot. Let's let u be x to the 1/2. Now, when you substitute, you want to make sure to replace all elements of your original equation that were in the old variable with the new variable. So, for instance, we want to replace all x's with u's. In this case, we're going to let u be x to the 1/2, and the main reason why we do that is because we see this x to the 1/2 here sitting sort of in the middle position where we would expect the single variable to sit if this were a quadratic equation. Now, if u is x to the 1/2, that lets us substitute for the x to the 1/2 part, of course, but we need to figure out how to substitute for x. So what we can do is we can manipulate this equation. If u is x to the 1/2, what we can try doing is squaring both sides to get u squared is equal to x, because x to the 1/2 squared. Remember that when you've got an exponent raised to an exponent, you multiply them together, and 1/2 times 2 is just 1, and x to the 1 is just x. So that means that u squared is x. That means that in the equation above, wherever we see an x, we can write a u. So after we substitute, we get u squared minus 6u, so x became u squared, x to the 1/2 became u, the constants stay the same, and so now we have the equation u squared minus 6u minus 18 equals 0. And now we've changed our original equation, which wasn't even a polynomial equation because it's got these fractional exponents, into a quadratic equation that we understand pretty well. And this one factors, so that's how we're going to solve it. So we need two numbers that multiply to equal negative 18 and add to equal 6. Let's see. 6 and 3 don't quite do it. 9 and 2, I think, were what I was thinking of when I prepared this. And so I am going to adjust this. I had miswritten this original problem. So everything I said before still holds. We're just going to do this with 7 instead of 6 there for that middle coefficient. Sorry about that. So we get u squared minus 7u minus 18 equals 0. So that gives us u minus 9 and u plus 2 equals 0. We could, of course, have done the other one, the one I miswrote, using the quadratic formula, but this is going to be much easier, so I would prefer to do it this way. So this tells us that u minus 9 equals 0, or u plus 2 equals 0. So we get u is equal to 9, or u is equal to negative 2. All right, so that means that we can go back and figure out what x is. So if u is x to the 1/2, that means that if u equals 9, that means x to the 1/2 is equal to 9. And if u is equal to negative 2, that means x to the 1/2 is equal to negative 2. So now we can try to solve for x in each of these cases. And again, we can do that by squaring both sides. So we can square both sides of x to the 1/2 equals 9 to get x equals 81. And we can square both sides of x to the 1/2 equals negative 2 to get x equals 4, 81 over here. And now, of course, we need to check these solutions. So we got two possible ones, x equals 81 and x equals 4. Let's plug them into the original equation and see what we get. So if we check 81, we'll plug 81 in for x, get 81 minus 7 times 81 to the 1/2 minus 18, and ask, does that equal 0? Well, remember that raising to the 1/2 is the same as taking square root. So 81 to the 1/2 is just the square root of 81, which is 9. So we get 81 minus, now 7 times 9 is 63. So we get 81 minus 63 minus 18, and we ask, does that equal 0? Well, yes, it does when you work that out, when you do that subtraction. 81 minus 63 minus 18 does in fact equal 0, and so that means 81 is a solution. Let's check 4. We want to see whether 4 minus 7 times 4 to the 1/2 minus 18, does that equal 0? Well, that gives us 4 minus 7 times 2, it's 4 to the 1/2 is the square root of 4. Yes, does that equal 0? We get 4 minus 14 minus 18. We ask, does that equal 0? And of course we see it doesn't. We get that the left-hand side works out to be negative 28, which is definitely not 0. So that means 4 is not a solution. Now, in this problem, there were actually 2 points where we might have arrived at an extraneous solution. The first is just doing substitution. Whenever you do a substitution, you run the risk of getting an extraneous solution, and you always have to go back and check your work. But we also had this step near the end where we squared both sides of an equation. That is also a case where you are often going to find yourself getting extraneous solutions. So there are 2 different places in this problem that make it so that you absolutely must check your solutions in order to see which ones of them work and which ones don't. So our answer for this problem is our solutions are x equals 81. That's the only solution. The solution set is the singleton set containing just 81.